Hello students, Straight here again. Today we're going to be studying and taking notes on section 11.2, speed and velocity. Here we see an illustration of a skater. A skater's speed might be measured in meters per second. All cars' speed would be measured in kilometers per hour. Couple different types of speed we deal with are instantaneous speed and average speed. Average speed will always be computed for the entire duration of a trip. Instantaneous speed measured only at a particular instant. We'll discuss more about each of these as we continue on. Definition of speed is just a ratio of the distance an object moves to the amount of time the object moves. Our SI unit of speed is meters per second. Definition for average speed is the total distance traveled divided by the time it takes to travel that distance. And then we have a formula for average speed. Total distance divided by total time, or we use symbol V bar equals D over T. Then we're going to be looking a little at some calculation problems dealing with average speed. Here we travel 35 kilometers in 0.4 hours, followed by 53 kilometers in 0.6 hours. What's your average speed? So as we always do, we're going to want to write down some information. In this case, our total distance D is 35 kilometers plus 85 kilometers, or 53 kilometers, which gives us 88 kilometers. Our total time, 0.4 hours plus 0.6 hours, gives us 1.0 hours. Then we want to come up with a formula, and we want to come up with what we're trying to figure out. So we're trying to find the average speed. V bar equals question, our formula, V bar equals D over T. Substitute in formula, and V bar equals 88 kilometers divided by 1 hour equals 88 kilometers per hour. And we got our new speed. Always think about, is your answer reasonable? Sometimes just by the type of whatever we're talking about, we can tell here 88 kilometers per hour, a reasonable speed for a car on the highway. Another problem. Here we got information given to us, gives us 4 kilometers in 32 minutes, 2 kilometers in 22 minutes, 1 kilometer in 16 minutes. So we pull that information out of the problem, and our distance becomes 4.0 kilometers plus 2.0 kilometers plus 1.0 kilometers, resulting in 4 plus 2, 6 plus 1, 7, 7.0 kilometers. The time given to us was 32 minutes plus 22 minutes plus 16 minutes. We add all that up and we get 50, 60, 70 minutes. And we do a little division using our formula. V bar equals d over t, so it's equal to 7.0 kilometers divided by 70 minutes, which is going to give us 0.10 kilometers per minute. Go a different way of writing it down. It's illustrated here. Same work, just a little different way of writing it down. Next problem. Very similar problem. We're still given some distance and time. We're still wanting to find our average speed. So trying to find the average speed. Formula is still distance divided by time. This time our distance is 190 kilometers plus 120 kilometers, which is 310 kilometers. Our time is 3 hours. 3 hours plus 2.0 hours, resulting in 5.0 hours. So the average speed is the 310 kilometers divided by the 5.0 hours, resulting in 62 kilometers per hour for our average speed this train travels. Again, a little different way of writing it out, same work. Another major type of speed is instantaneous speed. Instantaneous speed is the rate at which an object is moving at a given moment in time. Car's speedometer measures instantaneous speed. Speedometer will give, in the United States, we usually use miles per hour, but most speedometers also give kilometers per hour. Then we work a little bit with graphing and use what we call a distance time graph. And the slope of a line on a distance time graph is the speed. We use a lot of graphing as we're describing motion. Distance time graph, one of the types of graphs we'll use. Slope, defined to be the change in the vertical axis value divided by the change in the horizontal axis value. Steeper slopes indicate a higher speed, and slope you can think of just how steep the line is. Nice term you should have encountered in Algebra 1. Another phrase you would have counted in Algebra 1 for slope is rise over run. And we got some examples of some distance time graph here. And we say distance time. Distance is on the horizontal axis. Time is on the vertical axis. And we can look at between any 2 points on the line, how far does those things change, or how far does it rise and run. And we can figure out the speed, average speed over that interval of time. Another distance time graph, a little lower slope, a little lower speed. Speed on this one, dividing the 250 into 10, we get a speed or slope of 250 divided by 10 is 25 meters per second. Over here, dividing the rise and the run, we get 125 divided by 10, which is going to be 12.5 meters per second. And we got a third one here. Now this one has not a straight line, so its speed is changing. It starts at one speed here at 25 meters per second, and it kind of levels off, and it starts increasing again to a different speed. And we get a term we call velocity. Velocity, a description of both speed and direction. Velocity, a vector. So our last section we talked about displacement as a vector. Here velocity is a vector. So now we've had two vectors, both displacement and velocity. Speed is a scalar, like distance was a scalar in the last section. So sometimes knowing the speed isn't quite enough. We need to add that direction component and use the idea of a vector. The cheetah can go as fast as 90 miles or 90 kilometers per hour. If that would be its speed, if we wanted the velocity, we would add the direction it's moving in addition to that. So, vectors frequently used to show change in motion. We did the last section, we talked about we use vectors, we use little arrows, lines, to represent the vector. And the length of the line corresponds to how, in this case, how fast it's going, and then we have a direction associated with it too. So a longer vector represents a faster speed, a shorter one, a slower speed. Vectors can point in different directions to represent the direction. So, sailboat, as it changes directions, its velocity is changing, even though its speed is not changing. So if the direction changes, its velocity also changes, even as the speed stays the same. Then we can add velocities by using vector addition. You might deal with something like a boat on a river. The speed of the river is contributing to how fast the boat's moving and the actual speed of the boat. So we've got to combine those two things together. As in this case, in the first example, the river speed at 5 kilometers per hour, where the boat is going at 12 kilometers per hour. So the net speed of the boat is 17 kilometers per hour. If they were traveling in opposite direction, we would subtract it. Now, if the boat was trying to go across the river, we have to use a resultant vector. And there we see the 17 kilometers per hour. Here we see that resultant vector where we form a little triangle, and that resultant vector ends up being 13 kilometers per hour at that angle. It showed the direction. Couple quick review questions. Woman jogs 10 kilometers per hour, 10 kilometers in 1 hour, stops at a restaurant for 1 hour, then walks 10 kilometers in 2 hours. What was her average speed for the outing? So, if we're trying to do speed, we still want to look at distance divided by time. In this case, our distance, we had 10 kilometers and then 10 more kilometers. So we put those two together and the total distance was 20 kilometers. Time, we had 1 hour, another hour, and then 2 more hours. So 1, 1, 2 times going to be 4 hours. do a little division to get the speed. 20 kilometers divided by 4 hours is going to give us 5 kilometers per hour, as shown here. So plot time on the x-axis. We just draw a little quick thing here. We got time on the x-axis and distance on the y-axis. I'm just going to put a little d there. What does the slope of a graph represent? That's what we had earlier in the notes. Slope of a distance time graph is always going to represent the speed. This time Lisa plotted time in seconds on the x-axis. So we got the time in seconds. I'm just going to put the seconds there. And the distance in centimeters on this axis. And we went from 0, 0 to 10, 20. So we went from here to about, maybe somewhere like right there. So that's the one we're concerned with. So if we think of that term rise over run again, the rise is from 0, we went up to 20, so the rise is 20. The run, how far we go over, was 10 seconds, so 20 over 10 gives us 2 centimeters per second for the speed in this situation. Number 4, two velocities of an object are combined using. Straight definition here, we use vector addition. Yeah, number 5, we got a kayak moving across a stream. So in this case, the stream is flowing at 4 kilometers per hour. So we'll draw a little vector. Draw 4 kilometers per hour. Let's put a little 4 there. Then the boat's trying to go across at 3 kilometers per hour, so a little shorter. Connecting here, the boat's going to end up traveling in some manner, something like this. Give it our direction and our speed. So, looking at the choices we have over here, it's going to have to be a little bit longer than 4, so it might be 5 or it might be 7. Wouldn't be that much longer, because if we had the 4 and the 3, we get 7. So it's going to have to be the 5 kilometers per hour. Mathematically, you could use a thing called Pythagorean theorem to figure it out if we wanted to calculate it exactly. But here we'll just do a little approximation. If we'd have done it on the graph paper, could do a little measuring and figure it out also. And our last little question, SI unit for a speed of an airplane is miles per hour, and that would definitely be false, as miles is not SI. It would be kilometers per hour. So that completes our 11.2 notes. We'll see you next time when we look at 11.3 notes.